Welcome back. Today we're going to be studying 2.10 or graphs, structures in the graphs of functions. You're going to need your booklet, an erasable pen or pencil, and today we're going to need a ruler. If you don't have those, take a moment, go grab them. Now we're going to open up to 2.10 and take a look at a couple examples. Let's see what patterns we establish. For any particular polynomial, can we determine how many relative maxima, that is the highest point in a given area, and relative minima, or lowest point in a given area, we can find? Consider the following polynomial functions in factored form in the graphs. So look at that beautiful parabola, which is degree 2. It has 2 x-intercepts and 1 relative maximum or minimum. Here we have x times x times x, or x to the third, with 3 x-intercepts and 2, 1 max, 1 min, relative minima. Here we have x times x times x times x, or x to the fourth, so that's degree 4, with 1, 2, 3, 4 x-intercepts and 1, 2, 3, 3 maxima or minima. So it seems that the number of relative maxes and mins is 1 less than the number of x-intercepts, which is in turn the same as the number of degrees. But is that always true? Well, let's take a look at these over here. This is clearly degree 2. It has no x-intercepts, but it has 1 minimum. This right here, x squared times x, is degree 3 with 1 x-intercept, and as far as we can tell, no max or min at all. And this is x times x times x times x, so x to the fourth, with, let's see, 1, 2 x-intercepts, and only 1 minimum over there. So that very nice, clean rule of like, well, the degree is the number of x-intercepts, which is 1 more than the number of max or mins, clearly does not survive its encounter with reality. But is it completely useless? Well, not always. We can notice a couple things. The number of key movements or inflections seems to have a very close relationship to where the x-intercepts are. And by studying the behavior of the function inside the intercepts, we can actually start to predict very carefully what the shape of the graph itself looks like. So let's now look at example 3 on page 54. We're going to consider a function. Now notice this is a cubic, so it's degree 3. That also means it's going to behave something like this, right? And we can probably use factoring to figure out what the x-intercepts are, aside from one that has to occur. So we are told that x minus 4 is a factor of f to factor this polynomial. So if we want to factor this as x minus 4 as one of the factors, then I'm going to use what's called synthetic substitution, which is a form of writing long division, where you take the coefficients of what you're dividing, 1, negative 13, 44, negative 32, 1, negative 13, 44, negative 32. You take the opposite of what you're dividing by, and you basically do the same process. So 4 times 1 is 4. Leftover is negative 9. Negative 9 times 4 is negative 36. Leftover is 8. 8 times 4 is 32 with a remainder of 0. Which means that we can then reinterpret this function as x minus 4 times x squared minus 9x plus 8. Well, x squared minus 9x, x squared minus 9x plus 8 is not hard to factor. That's x minus 1 times x minus 8. And therefore the x-intercepts, one of which for each factors are where the factors themselves are equal to 0, must therefore be at x equals 4, so that's 4 comma 0, at x equals 1, 1 comma 0, and at x equals 8, 8 comma 0. Now, at which values can the function change from being positive to negative or from negative to positive? So if you imagine our graph, we want to know where can it change from being positive to negative or negative to positive. Well, you can only do that when it's going through the x-axis at the x-intercepts. So if we consider the x-intercepts, if we want to sketch that graph, we can look at where the function is positive or negative on the 4 intervals, where x is less than 1, x is between 1 and 4, x is between 4 and 8, and x is greater than 8. And the reason for that is because 1, 4, and 8 are the only places where they can cross over the x-axis, where the behavior can go from being positive to negative. So if we can imagine, these are our intercepts, if we can see what's going on in between each of these intervals, we can then interpret what the graph should roughly look like. Since the x-intercepts are the only location the function f of x can change from positive to negative, we can go ahead and tell what the behavior is in between the two by simple substitution. So if I substitute a value less than 1, for example 0, into this equation, f of 0 is negative 32 or negative. Now if I substitute a value in between 1 and 4, pick any number you like, let's say 2, you'll find that the output is positive. Then if again I substitute in a value between 4 and 8, let's say 5, you find the answer is negative. And then if I substitute in a value greater than 8, let's say 10, you find the answer is again positive. Which means that when the graph is less than negative 1, or x is less than 1, it's below the x-axis. Between 1 and 4, it's above the x-axis. Between 4 and 8, below again. And between greater than 8, it's higher than. That means we can actually create a fairly accurate graph or sketch of the x-axis. So I'm going to use my handy dandy ruler here to draw in my x-axis. There we go. And then I'm going to draw in this direction right here. There we go. There's my y-axis, and I'm going to mark my 1, my 4, and my, let's see, 4, 5, 6, 7, 8. Those are my x-intercepts. And I know cubics start off negative. Then they go up, 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 positive. Then they're going to come down, negative. Then up, up, again positive, again going through the x-axis. Now we're going to compare this graph with one from a graphing utility like Desmos, and compare the sketch. Once you find the sketch, you'll find that the shape in general is about right. What will be different is where these maxima and minimum are in terms of their x values. And that, well, that is something we will talk about how to clean up in our next lesson. Wishing you a wonderful rest of your day.